Welcome back to the deep dive. Today, we are not just zooming out. We're zooming out as far as it is physically and mathematically possible to go. We're talking about the whole thing.
The whole thing.
The whole enchilada.
And by enchilada, you mean the universe.
I mean the universe.
Yeah.
The origin, the fate, the beginning of time, the end of time, and everything in between. We are looking at the work of Stephen Hawking, specifically his obsession with the Big Bang and, what it actually means for reality.
It's a massive topic. And frankly, the source material we have today, articles, Hawking's own lectures, the historical context, it really challenges a lot of the intuition we have about how the world works.
Oh, for sure.
We're going to be talking about time flowing sideways, energy that equals zero, and why you and I are, well, technically nuclear waste.
I love being nuclear waste. But before we get into the physics, we have to set the stage with a story that I think just captures the tension of this whole discussion perfectly. It takes us back to 1981.
Right. Rome, the Vatican.
Exactly. The Jesuits had organized a cosmology conference. Now, just pausing there for a second, the idea of the Vatican, organizing a conference on the origins of the universe, it feels like the setup to a very intellectual bar joke.
It does, but, the Jesuits have always been the intellectuals of the Catholic Church. They care deeply about science. But the history there, it's heavy.
Heavy is a very polite way to put it.
It is, and Stephen Hawking, who was attending this conference, was acutely aware of that weight. He actually points out this historical coincidence that I find just fascinating.
Oh, yeah.
Hawking was born exactly 300 years after the death of Galileo.
To the day.
To the day. And for Hawking, that wasn't just some calendar quirk. He really felt a connection there. Galileo was the guy who effectively got house arrest for life because he dared to tell the church that the Earth wasn't the center of the universe.
He brought math to a theological fight.
He did. So 300 years later, Hawking is rolling his wheelchair into the Vatican to meet Pope John Paul II. The atmosphere has obviously changed. Nobody's getting burned at the stake, but there are still boundaries.
Distinct boundaries.
Very distinct. The Pope grants the scientists an audience. It's all very cordial. But during this audience, the Pope gives them a specific directive. He tells them, essentially, we support your science. You are free to study the evolution of the universe after the Big Bang.
Okay, so how galaxies formed, how stars burn, chemistry, biology, that's all fair game.
All fair game. That's the clockwork. But the Pope said they were not to inquire into the Big Bang itself.
Don't touch it. Draw the line.
Exactly. Because in the Church's view, the Big Bang, that moment of singularity, that is the moment of creation. That is where God touches the physical world. It's the work of God. To probe that moment is to overstep.
And this is where the irony just becomes so delicious, because the Pope is giving this instruction to Stephen Hawking, of all people.
And the Pope has absolutely no idea what Hawking had just done. Just hours before this meeting, Hawking had given a talk at the conference. And he hadn't just inquired into the Big Bang.
Yeah.
He had presented a paper proposing the no-boundary theory.
Which we are definitely going to unpack later. But the headline of that theory is essentially what?
The headline is that the universe has no boundary, no edge, and critically, no beginning.
So while the Pope is saying, don't touch the beginning because that's God's moment, Hawking is sitting there thinking, I just mathematically suggested that that moment doesn't even exist.
He was effectively erasing the moment of creation from the timeline. So Hawking sat there, presumably keeping a very straight face, thinking about Galileo and just hoping he wouldn't be the next one to get silenced.
It really frames the mission of what we're doing today, doesn't it? This isn't just dry physics. This is the struggle to understand if there was ever a start button.
It's the ultimate question. We have these two main theories in physics: general relativity, which handles the big stuff like gravity and galaxies, and quantum mechanics, which handles the tiny stuff.
And they hate each other.
They notoriously do not get along. General relativity predicts a distinct beginning, a singularity. Quantum mechanics suggests something much, much fuzzier.
So our job today is to try and bridge that gap. We're going to walk through the standard hot Big Bang model, the one everyone kind of learns in school. Then we're going to smash it apart and look at all the problems with it. We'll talk about inflation. We'll wrestle with the anthropic principle. And then finally, we're going to try to wrap our heads around that no boundary proposal.
And the goal really is to see if we can answer, does the universe have a beginning? Or does it just be?
Let's start with the classic model, the standard hot Big Bang. This is the Friedman model.
Right. Alexander Friedman. He was the one who proposed that the universe is expanding. And the key mechanism driving the entire history of the universe in this model is cooling.
I think we need to pause on cooling for a second. Because when I think of cooling, I think of putting leftovers in the fridge. But in astrophysics, cooling is doing a lot of heavy lifting. What does it actually mean for the universe?
It's a great question because our intuition really fails us at these scales. Temperature, at a fundamental level, is just a measure of the average energy, or you could say speed of particles.
So hot just means fast.
Hot means chaotic, zooming, crashing speed. Cold means sluggish, slow.
Okay. So
Now, in the universe, there are these forces that want to pull particles together. You have the strong nuclear force, which wants to stick protons and neutrons together.
right.
You've got the electromagnetic force, which wants to stick electrons to nuclei. Gravity wants to stick everything together.
The forces are the glue.
They are the glue.
Yeah.
But if the temperature is really high, the particles are moving so fast that the glue just can't hold. They smash into each other and they just bounce off. It's like trying to play a delicate game of cards in the middle of a mosh pit.
Too much kinetic energy.
Exactly. So when we say the universe cooled, what we really mean is that the particles slowed down enough for the glue to finally stick. The whole history of the universe is a history of things slowing down enough to bond.
That makes perfect sense. Now, there's also this concept of phase transitions mentioned in the source material. It talks about particles and antiparticles being produced and annihilated. Can you unpack that for us?
Yeah, this is crucial for the very, very early universe. We're talking milliseconds. At extremely high temperatures, energy can spontaneously turn into matter.
EMC war.
That's the one. You have so much pure energy that it just pops into existence as a particle and an antiparticle pair. But because it's so dense, they almost immediately crash into each other and annihilate right back into energy.
So it's like a constant, violent, flickering static.
That's a great way to think of it, a cycle of creation and destruction. But as the universe cools, the energy level drops. And suddenly, you don't have enough energy to create new pairs anymore.
But the annihilation still happens.
The annihilation still happens. So the pairs wipe each other out, and you're left with, well, mostly radiation and a tiny bit of leftover matter.
Okay, so let's look at the timeline. Because the speeds and temperatures here are just mind-boggling. We start at the singularity. Zero size. Infinite heat.
Which is where the math of general relativity just breaks. It gives you an error message. It just says infinity.
So let's move to 1 second after the Big Bang. Just 1 second. The temperature's dropped, but it's still warm.
Warm is the understatement of the century. At 1 second, the temperature is about 10 billion degrees.
10 billion.
That is 1,000 times hotter than the center of our sun. The only thing we have on Earth that even approaches that is the very center of a hydrogen bomb explosion.
So at 1 second old, the entire universe is a hydrogen bomb fireball.
Correct. And in this fireball, matter as we know it, atoms, molecules that just can't exist. It's mostly photons, which is light, electrons, and these things called neutrinos.
Neutrinos. Those are the ghost particles, right? They just fly through everything.
Yes. They are absolutely fascinating. They have almost no mass, no electric charge. They pass through the Earth like it's not even there. But in the early universe, they were everywhere.
And the source material brings up a really interesting point about them regarding dark matter. We're always hearing about the missing mass of the universe.
Right. We look at how galaxies spin, and they spin way too fast. There isn't enough visible matter to hold them together with gravity. They should just fly apart.
So we assume there's this invisible dark matter holding them together.
Exactly. And neutrinos are a prime suspect. Even if they have a tiny, tiny sliver of mass, and recent evidence suggests they do, there are so many of them left over from the Big Bang that their combined weight could account for all that missing gravity.
So they could be the invisible scaffolding of the entire universe.
They could be. It's a very compelling idea.
Okay, moving the clock forward again. We are now at 100 seconds after the Big Bang.
The temperature has now plummeted to 1 billion degrees.
Still pretty toasty.
It's the temperature of the very hottest stars. But this is a critical threshold. At 1 billion degrees, the protons and neutrons have finally slowed down enough. The mosh pit has calmed down.
And the strong nuclear force can finally grab them.
Yes. This is the first real clumping. A proton and a neutron smash together and they stick. They form deuterium, which is just heavy hydrogen. Then those deuterium nuclei smash together to make helium.
And this isn't a small amount of helium we're talking about, right?
No, not at all. The calculations show that about 25% of all the protons and neutrons in the universe were converted into helium in just these first few minutes.
That seems like a very specific number. 25%.
It is. And it's one of the most powerful pieces of evidence we have for the Big Bang Theory. When we look out at the universe today, at the oldest stars, at primordial gas clouds, we see that ratio everywhere. The universe is about 25% helium by mass.
So the theory predicted the number, and then our observations confirmed it.
Exactly. It's a beautiful piece of science.
Speaking of predictions, we have to talk about the paper that first predicted this whole hot soup phase. The Alpher Beta Gamma paper.
The Alpha Beta Gamma paper.
This is just proof that physicists are nerds who love a good pun.
Oh, absolutely. So George Gamow is this brilliant Russian-American physicist. He's writing this paper with his student, Ralph Alpher. But Gamow looks at the author list, Alpher, Gamma, and he thinks, that sounds okay, but you know what would be better?
He wants the Greek alphabet.
He wants Alpha, Beta, Gamma. So he just calls up his friend Hans Bethe, a famous nuclear scientist who hadn't written a single word of the paper, and just asked to put his name on it, just for the joke.
Did Bethe?
Bethe was a good sport about it. And it was kind of fitting because the paper was about the beginning of everything, alpha. But jokes aside, this paper from 1948 made a massive, massive prediction.
And what did they predict?
They argued that if the universe started in this super hot, dense state, that heat couldn't just vanish into thin air. As the universe expanded, that radiation would get stretched out and cooled down, but it should still be there.
Like an echo, a ghost of the heat.
Exactly. A background hum. They predicted a background radiation of microwave energy just a few degrees above absolute zero, filling the entire sky.
But nobody could find it for years.
This technology just wasn't there yet. Until 1965. Enter Penzias and Wilson.
This is my favorite accidental discovery story in all of science. These guys weren't looking for the origin of the universe, were they?
Not at all. They were working for Bell Labs in New Jersey. They had this massive horn antenna, and they were just trying to communicate with early satellites. But they had a problem.
A noise.
A persistent, low-level, static hiss. It was there day and night. It was there no matter where they pointed the antenna. They did everything they could think of to get rid of it. They checked the wiring. They checked for interference from New York City.
And they checked for pigeons.
They did.
Yep.
A pair of pigeons had been nesting in the antenna, so Penzias and Wilson climbed up there. They caught the pigeons, and they cleaned out the white dielectric material, as they so delicately put it in their paper.
Bird poop. They scrubbed the bird poop.
They scrubbed the bird poop. But the noise was still there.
And that noise was the universe.
That hiss was the cosmic microwave background. They were listening to the photons left over from the fireball of the Big Bang, stretched out over 13 billion years. That discovery effectively killed all the competing theories. The hot Big Bang was real.
So we have the explosion, we have the soup, we have the helium. But a soup isn't a galaxy. A soup isn't a planet. How do we get from a hot uniform fog to structure?
We enter the era that cosmologists somewhat uncharitably call the boring million years.
Great branding. Coming up next. Nothing happens for a really long time.
It's pretty accurate, though. After the helium forms, the universe just expands and cools. The electrons get captured by the nuclei to form neutral atoms. The fog clears. But mostly it's just dark gas getting colder and colder.
But it wasn't perfectly uniform, was it?
No, and thank goodness for that. There were tiny, almost infinitesimal irregularities, little lumps in the cosmic porridge.
I mean, gravity loves a lump.
Gravity is an amplifier. If one region is just slightly denser than its neighbor, it has slightly more gravity. That gravity then pulls more matter in, which makes it even denser, which creates even more gravity.
It's a runaway effect.
It is, a feedback loop. The expansion of the universe is trying to pull everything apart, but in these dense regions, gravity wins. The expansion slows down, it stops, and then it reverses. The gas starts to collapse inward.
And this collapse leads to rotation. I want to visualize this. Why does it start to spin?
Think of a figure skater. This is the classic physics analogy because it just works perfectly. When a skater is spinning and she pulls her arms in tight, what happens?
She spins faster. Conservation of angular momentum.
Exactly. These massive gas clouds had just a tiny bit of random rotation to begin with. As they collapsed under gravity pulling their arms in, they spun faster and faster and faster.
And things that spin fast tend to flatten out.
Right. Centrifugal force pushes outward at the equator, so the cloud flattens into a disk. That's how we get beautiful spiral galaxies like our own Milky Way.
And what if they don't spin fast enough?
They don't flatten, they just become elliptical galaxies. big sort of oval blobs of stars without that beautiful spiral structure.
So the galaxies form, then the gas inside them collapses further to form stars. And this brings us to the chemistry of life, because the Big Bang gave us hydrogen and helium. But I'm looking at my hand, and it's made of carbon. I'm breathing oxygen. Where did that stuff come from?
We are, quite literally, nuclear waste.
Put that on a t-shirt. I'd buy it.
The first generation of stars formed from that pure hydrogen and helium. They were massive, hot, blue monsters. And in their cores, the pressure was so intense that they started crushing atoms together. Fusion.
They turned hydrogen into helium.
And then helium into carbon. And carbon into neon, oxygen, silicon, all the way up the periodic table. They were elemental factories. But they eventually hit a wall. Iron.
Why is iron the wall?
Because fusing iron doesn't release energy, it actually consumes it. So once a star's core starts making iron, the engine dies. The outward pressure of heat stops instantly. Gravity wins. The star collapses and then rebounds in a massive explosion, a supernova.
And that explosion does the delivery work.
It flings all those heavy elements, the carbon, the oxygen, the gold, all of it, out into the galaxy. They mix with the interstellar gas clouds.
And then a second generation of stars forms from that enriched gas.
Or a third generation, like our sun. Our sun formed about 5 billion years ago from gas that was already contaminated with the debris of countless dead stars. And because of that debris, we could form rocky planets, we could form Earth.
It's so humbling. Every atom in your body, other than the hydrogen, was cooked inside a star that died billions of years before Earth even existed.
We are ghosts of dead stars.
Let's just touch briefly on the origin of life, because the source material mentions it to complete the timeline. We have the Earth. But early Earth was not a garden.
It was a hellscape. No oxygen at all. The atmosphere was mostly hydrogen sulfide.
Rotten egg gas. Lovely.
Poisonous. But in the oceans, primitive macromolecules formed. Things that could just, by chance, copy themselves.
And here, the key concept is error.
Yes. We usually think of errors as a bad thing. But in evolution, errors are the engine. If those first molecules copied themselves perfectly every single time, nothing would ever change. You'd just have soup forever.
So mistakes were made.
Mistakes were made. A copying error led to a molecule that was slightly better at surviving, or maybe one that, by chance, started consuming that hydrogen sulfide and releasing oxygen as waste.
Which eventually terraformed the entire planet.
It created the very atmosphere we breathe.
So that's the standard story. Big Bang cooling, clumping stars, supernovas. It's a neat narrative. It fits on a bumper sticker, but if you look closely, the sticker is peeling. This model has problems. Big ones.
It does. It explains a lot, but it fails to answer 3 very specific, very annoying questions. We call them the horizon problem, the flatness problem, and the density problem.
Okay, let's break them down. Problem number 1, uniformity, the horizon problem.
Right. So go back to that cosmic microwave background radiation. We look at the sky in one direction, we measure its temperature, then we look at the sky in the exact opposite direction.
180 degrees away.
Effectively, 27 billion light years apart when you account for expansion. And we measure the temperature there. They are exactly the same, down to 1 part in 100,000.
Okay, I'm going to play devil's advocate. Why is that a problem? Why shouldn't they be the same?
Think about a cup of hot coffee and a glass of cold milk sitting on opposite sides of a giant auditorium. If you don't touch them, they will have different temperatures. To get them to be the exact same temperature, they have to interact, you have to mix them. Heat has to flow from the hot one to the cold one.
And that takes time.
In the universe, the fastest anything can travel is the speed of light. If you calculate the age of the universe when that light was emitted, there literally hasn't been enough time for a beam of light to get from one side of the sky to the other.
So those two regions have never met.
They have never been in causal contact, so how do they know to be at the same temperature? It's like walking into 2 classrooms on opposite sides of the planet and finding 2 students who wrote the exact same essay word for word.
You'd assume they cheated, that they communicated.
You would absolutely assume they communicated. But under the standard Big Bang theory, communication was impossible. That's the horizon problem.
Problem number 2, the flatness problem. This one freaks me out a little bit.
This one is all about fine-tuning. The universe is expanding. Gravity is trying to pull it back together. It's a cosmic tug-of-war.
And the balance seems to be suspiciously perfect.
It's terrifyingly perfect. Scientists calculated the rate of expansion 1 second after the Big Bang. If that rate had been smaller by even 1 part in 100,000 million...
Hold on. Let me just visualize that. One part in a one with 17 zeros after it.
That's right. If the expansion had been that much slower, the universe would have recollapsed into a big crunch before it ever reached its current size.
So crunch. Game over.
Ugh.
No us.
And if it had been faster by that same tiny fraction, it would have flown apart so fast that stars and galaxies never would have had time to condense. It would just be a cold, empty dark.
So we are walking on a razor's edge.
We are balancing on the blade of a knife, and the standard model has no explanation for why. It just says, well, I guess we got really, really lucky.
And scientists hate luck.
We hate luck. We want a mechanism. We want a reason.
And that brings us to problem 3, density fluctuations.
Right. We said earlier that gravity amplified these little lumps in the early universe to make galaxies, but where did the lumps come from in the first place?
The standard theory says the early gas was almost perfectly uniform.
Exactly. If you have a perfectly smooth tank of gas, it doesn't just spontaneously decide to get dense in one spot. The model doesn't explain the origin of the seeds that grew into galaxies.
So we have a model that works great, provided you accept a miraculous coincidence in temperature, a miraculous coincidence in expansion speed, and a bunch of unexplained lumps that just happen to be there.
It suggests that the initial state, the way the universe was set up at the very beginning, was chosen with just incredible, unbelievable precision.
Which leads us to the philosophical band-aid, the anthropic principle.
We see the universe the way it is because we exist.
Every time I hear this, I feel like it's a cop-out. You know, why is the sky blue? Because if it wasn't, you wouldn't be here to ask the question.
Yeah.
It feels totally circular.
It is circular, but there are nuances to it. There's a weak version and a strong version.
Okay, walk me through the weak anthropic principle.
The weak principle is actually pretty defensible. It basically says, look, the universe is huge. Maybe it's infinite. The conditions probably vary from place to place. Maybe some parts are hot, some are cold, some are dense, some are empty.
Okay.
Intelligent life like us requires very specific conditions: carbon, warmth, liquid water, stability. So by definition, we can only evolve in the regions of space-time that happen to have those conditions.
The Goldilocks zones.
Exactly. So we shouldn't be surprised to find ourselves living in a hospitable region. The analogy Hawking uses is a rich person living in a wealthy neighborhood. They shouldn't be surprised they don't see poverty at their window, because if they lived in a poor neighborhood, they wouldn't be rich.
That makes sense, and it explains things like the age of the universe. Like, why is the universe 13.8 billion years old?
Because you can't have humans in a 1 billion-year-old universe. You need time for the first stars to live, die, cook the carbon, and then for new solar systems to form. So our very existence sets a lower limit on the age.
But then there's this strong anthropic principle.
This is the really controversial one. It claims that there are many different universes, a multiverse, and in each one, the fundamental laws of physics are different.
So in universe A, gravity pushes instead of pulls. In universe B, electrons weigh as much as bowling balls.
Exactly. And in almost all of those universes, complex structures can't form. No stars, no planets, no life. We just happen to exist in the one kind of universe that allows for life. So in a sense, the universe exists for us.
Hawking did not like this.
No. He had two main objections. First, Occam's razor. If those other universes are completely separate and we can never, ever observe them, do they really exist in a scientific sense? Adding a billion invisible universes just to explain our one visible one is messy.
It's not an economical theory.
And second, it just feels like a huge step backward historically. We used to think Earth was the center of everything, then the sun. Then we realized we are on a minor rock around an average star in the suburbs of a pretty average galaxy.
We aren't special.
The whole history of science is learning we aren't special. The strong anthropic principle tries to make us special again. It says the whole design of the cosmos revolves around our existence. And Hawking found that very hard to swallow. He wanted a physical mechanism, not a philosophical one.
Enter Alan Guth and the concept of inflation.
This is the superhero of modern cosmology. In 1980, Guth proposed that the early universe didn't just expand, it inflated.
What's the difference?
Speed and violence. He proposed that for a tiny, tiny fraction of a second, the universe expanded exponentially. The radius increased by a million times.
That's a one with 30 zeros, actually.
30 zeros in less time than it takes to blink.
How? What fuels an explosion like that?
Supercooling. And to understand this, we need to think about water.
I love water. Let's do it.
You can actually cool pure water below freezing, below 0 degrees Celsius, without it turning to ice immediately, if it's very pure and kept very still. It's called supercooling. It's an unstable state.
It wants to freeze, but it hasn't figured out how yet.
Exactly. It has all this latent heat energy trapped inside it. Guth suggested the universe did something very similar. As it cooled, the fundamental forces, the strong, weak, and electromagnetic forces, were supposed to separate. They were supposed to freeze into their distinct forms.
But they got stuck.
They got stuck in that high-energy unified state for just a moment too long. This creates a massive amount of excess energy. And in general relativity, this specific type of trapped energy has a very weird property. It acts like anti-gravity. It pushes violently. It causes an accelerating exponential expansion. That's inflation.
So the universe kind of holds its breath, gets stuck, and then whoosh.
And this incredible whoosh solves our 3 big problems.
Okay, let's check the scorecard. The flatness problem, the razor's edge.
Inflation solves this by brute force. Imagine you have a balloon that is all wrinkled and crumpled. Now, in an instant, blow it up to the size of the Earth.
From my perspective on the surface, it would look perfectly flat.
Exactly. The expansion is so enormous that it stretches out any initial curvature to the point of being undetectable. It drives the universe automatically toward that critical balance. We don't need luck. The mechanism forces flatness.
Okay, what about the horizon problem? The 2 students who cheated on the test.
Inflation says that before the whoosh, the entire observable universe was tiny, microscopic.
So it was small enough for light to travel across it and even things out.
Yes, the different regions had plenty of time to mix and mingle. They equalized their temperature, they compared notes, and then inflation grabbed them and ripped them billions of light years apart.
So they look like they cheated, but really they just shared the answers before the test started.
That's a perfect analogy.
Now, there is one concept in inflation that I really need you to walk me through carefully, because it sounds like magic. Guth calls it the ultimate free lunch.
It's my favorite concept in all of physics.
The source material says the total energy of the universe is 0. How can that be? I have mass. The Earth has mass. The sun is huge. EMC at 2i means that all that mass is energy. That's a lot of positive energy.
It is a huge positive number on the balance sheet.
So how can the total possibly be 0?
You have to look at the whole balance sheet. On the asset side, you have matter and all its energy. That's positive. On the liability or debt side, you have gravity.
Why is gravity a liability? Why is it negative energy?
Let's use an analogy. Imagine you want to build a hill. You have to dig a hole to get the dirt. The pile of dirt is your matter. That's your positive mass.
Okay.
But to make that pile, you have to create a hole. That hole represents the gravitational field. Gravity is attractive. To separate 2 things, to pull the dirt out of the hole, you have to do work. You have to put energy in.
So the separated state implies a kind of energy debt.
Exactly. If you want to get rid of the pile of matter, you just shove it back into the hole of gravity. What do you have left?
Flat ground. Nothing.
0.
Yeah, 0.
The universe is a way of borrowing energy from gravity to create mass. Hawking and Guth argue that if you sum up all the matter energy, positive, and all the gravitational potential energy, negative, they cancel out perfectly.
So during inflation, when the universe doubles in size,
It doubles the amount of matter, which sounds like it violates conservation of energy.
Mm-hmm.
But it also doubles the size of the gravitational field. It doubles the debt.
The hole gets deeper as the pile gets higher.
And the net sum always stays at 0. That's the free lunch. You can create an entire universe out of literally nothing, energetically speaking, as long as you balance the books with gravity.
That is profoundly elegant and also slightly disturbing.
It takes the miracle out of creation. You don't need an infinite amount of energy to start the universe. You just need 0.
So inflation fixes the big problems. It explains the bang.
Yeah.
But we still have an issue, don't we?
The singularity.
Even with inflation, if you rewind the tape all the way back, you still hit a point where the universe is infinitely small and infinitely dense. And as you said before, general relativity just crashes there.
It does. Inflation pushes the problem way, way back, but it doesn't solve the absolute beginning. To do that, we have to leave the comfortable world of general relativity behind. We need quantum gravity.
This is section 6, the deep end of the pool.
This is where Hawking really enters his element. He knew that to handle the singularity, you have to start treating the entire universe like it's a quantum particle.
And to do that, he used this approach from Richard Feynman, sum over histories.
Right. Now, in our normal everyday lives, or in classical physics, if a ball rolls from point A to point B, it takes one path, a straight line, and maybe a curve if you throw it.
One history.
But Feynman said, in the quantum world, that's just wrong. A particle doesn't just take one path. It takes every possible path.
Wait, every path? You mean a particle goes from A to B by way of the Andromeda galaxy?
Yes. It takes the straight path. It takes the curly path. It takes a path that loops around the moon and comes back. It takes them all simultaneously.
That sounds completely insane.
It is insane, but the math works perfectly. To calculate the probability of where the particle will actually end up, you have to add up the waves associated with all of those possible histories.
The sum over histories.
Now, Hawking said, let's apply this to the universe itself. The universe doesn't have a single history. It has every possible history.
But to do that math, the source material mentions this thing called imaginary time. You need to explain this very carefully, because when I hear imaginary time, I think of Alice in Wonderland. Or, something I tell my boss when I'm late. Sorry, I was stuck in imaginary time.
It's a terrible name. It sounds like make-believe. But in mathematics, imaginary numbers are very real and very useful. They're just a different direction.
Give me a visual.
Okay. Picture a graph. You have horizontal line, left to right. That's real time. Past on the left, future on the right.
Yep, got it.
Now draw a vertical line going up and down, perpendicular to the first one. That is imaginary time. It's just another coordinate, like north-south versus east-west.
So why do we need it? What does it do?
Because in real time, there is a fundamental, unbreakable difference between space and time. You can move back and forth in space, you can walk to the store and then walk back home, but you can't walk back in time. Time always flows forward.
Time is a one-way street.
It is. But in imaginary time, that distinction vanishes. In the equations using imaginary time, the time coordinate behaves exactly like just another direction of space. It's not special anymore.
So instead of having 3 dimensions of space and 1 of time, you effectively have 4 dimensions of space.
We call it Euclidean space-time. Exactly. And this mathematical trick allows Hawking to do something absolutely incredible. It allows him to propose the no-boundary condition.
This is the climax of the theory, the no-boundary proposal.
Right. In classical theory, using real time, the universe starts at a singularity. You can think of it like a cone. As you go back in time, the cone gets narrower and narrower until it comes to a sharp, jagged point.
The point, the singularity, the beginning.
And that point is a boundary. It's an edge. The laws of physics stop working there. You fall off the edge of the map.
Okay.
Hawking says. But if you look at the universe in imaginary time, it doesn't look like a cone. It looks like a sphere. Or, more accurately, the surface of a sphere, like the Earth.
A sphere. Okay. Let's use the Earth analogy.
Think of the history of the universe as latitude on Earth. The beginning, the Big Bang, is the North Pole.
Okay, so I'm standing at the North Pole. It's a single point.
Right. It's a point where all the lines of longitude meet. Now ask yourself the question, what is north of the North Pole?
There isn't anything north of the North Pole. The lines they just converge there and then they go south.
Exactly. But is the North Pole a singularity? Is it a jagged edge where the laws of geography break down? Is there a sign that says, end of the world, turn back now?
No. It's just a regular point on the ice. The geometry is perfectly smooth.
Precisely. That is the breakthrough. In the no-boundary proposal, the beginning of the universe is like the North Pole. It is a point where time starts, but it is not a boundary. The laws of physics hold perfectly well there. The universe just closes in on itself like a smooth sphere.
So if you ask the question, what happened before the Big Bang? It's like asking, what is a mile north of the North Pole? It's not a deep mystery. It's just a grammatically nonsensical question within this specific geometry.
Correct. The universe has no boundary. It has no edge. It is completely self-contained. It doesn't start in the traditional sense of a sudden creation event. As Hawking so beautifully put it, it would neither be created nor destroyed. It would just be E.
It is. That's a mind-bending idea. It effectively removes the start button from the control panel of the universe.
It removes the singularity. And without a singularity, you don't need an external agent, a creator, to step in and set the initial conditions. The universe sets its own conditions just by having the geometry of a closed shape.
This sounds amazing mathematically. It's incredibly elegant.
Mm-hmm.
But is it real? Or is it just a nice mathematical trick? Because science needs proof. It needs to be testable.
That is Section 7, verification. A theory is only a good scientific theory if it predicts something we can actually go out and check.
And for this, we go back to our old friend, the cosmic microwave background.
Yes. The no-boundary proposal, when you combine it with the uncertainty principle of quantum mechanics, gives a very specific prediction. It says the universe couldn't have started off perfectly smooth. It had to have ripples.
Because quantum mechanics says nothing can ever be perfectly still or perfectly uniform.
Right. There are always little quantum jitters. And the theory predicts exactly what kind of ripples. It predicts the spectrum of the fluctuations, how many big lumps there should be versus how many small lumps.
And inflation would then take those tiny quantum shivers and blow them up to the scale of galaxies.
Exactly. So in 1992, NASA launched the COBE satellite, the Cosmic Background Explorer, to look for these exact tiny temperature ripples in the background radiation. They found them. And the pattern of the ripples, the spectrum, it matched the predictions of inflation, plus the no-boundary proposal, almost perfectly.
That is a genuine mic drop moment for cosmology.
It is. Hawking later said that these ripples were the fingerprints of creation. The theory was put to the test, and it survived.
But there's still this lingering confusion for me, and I think for a lot of people listening too. We live in real time. I check my watch, I get older. In real time, there's a big bang. There was a beginning.
This is the final philosophical twist. The clash between real time and imaginary time.
And Hawking seems to almost say, real time is the illusion.
Well, he adopts a philosophy he calls model-dependent realism. He argues that physics is just a mathematical model we build in our minds to describe our observations, and it's meaningless to ask if a model is real.
The only question is, which model is more useful?
Exactly. Real time is the model that describes what we experience, birth, death, the passing of hours. But that model of real time leads to a singularity where physics breaks down. It fails as a fundamental theory.
Whereas imaginary time.
The model using imaginary time describes a universe that is completely self-contained, follows the laws of physics everywhere, and has no nasty singularities. So Hawking argues that imaginary time might just be the more fundamental description of reality.
So that implies that what we perceive as linear time with a distinct beginning is just a perspective, a filter our brains use. But the underlying structure is this timeless, closed sphere.
It's finite in extent, but it's unbounded, just like the surface of the Earth.
This brings us all the way back to where we started, to the Vatican, the Pope, and God.
The conclusion, the theological implications.
The Pope's view was the traditional one. God stands outside the universe. He winds up the clockwork. He chooses the initial state. He pushes the button.
That view relies on there being a boundary, a moment of interaction, a distinct beginning where an outside force can act.
But if the no-boundary proposal is correct,
then there is no edge. There is no moment where the clock was wound up. The universe is a closed system.
So Hawking asks the final provocative question. If the universe contains itself perfectly, has no beginning and no end, and simply is, then what is the place for a creator?
He's not necessarily saying God doesn't exist, but he is saying that the job description for a creator is severely reduced. There's no lighting the fuse for a creator to do.
It seems to transform the idea of God from a clockmaker who starts things to maybe the laws of physics themselves.
Einstein often took that view. Spinoza's God. God is the underlying logic and beauty of the universe. Hawking seems to land in a similar place. If the physics is entirely self-contained, the miracle isn't the start of the universe. The miracle is that there is a universe at all.
He asks, why does the universe go to all the bothers of existing?
That is the famous quote. The math can explain how it exists. It can describe the sphere, the imaginary time, the inflation. But the math can't breathe fire into the equations and make a universe for them to describe.
It can't explain why there is something rather than nothing.
And that is a question that even the no-boundary proposal can't answer. That, he suggests, is for the philosophers. Or maybe the theologians.
I think that is a perfect place to leave it. We've gone from the Vatican to the mosh pit of the early universe through the boring million years, dug a hole to pay for the free lunch of inflation, and landed on a timeless sphere where north of the North Pole doesn't exist.
It's a journey that takes us from the very tangible, bird poop on an antenna to the utterly abstract. But that's Hawking's gift, isn't it? He shows us that the abstract math is what allows the tangible universe to exist.
I'm going to be thinking about that digging the hole analogy all week, the idea that gravity is just the debt we pay for existing.
We're all just living on borrowed energy.
Thank you for guiding us through the quantum foam today.
Always a pleasure to explore the infinite.
And to you, listening, next time you look up at the stars, Remember, you're looking at the debris of a nuclear explosion, smoothed out by inflation, existing in a universe that might just be a finite sphere in imaginary time. No big deal.
Just another Tuesday in the cosmos.
Thanks for listening to The Deep Dive. Keep wondering.